Welcome everyone to part 3 of my overview of some of the results of my thesis, Structural Degeneracy in Neural Networks. And so picking up from last time, today I'm going to present the proof of the sort of big result in the thesis, which is on the NP completeness of computing the approximate degeneracy, the parametric approximate rank of a simple single hidden layer tanh neural network. So the basic structure that I have planned for today is a very quick recap of the definitions that we need. So this family of neural networks, the rank, the approximate rank, the parametric approximate rank, and also the concept of NP completeness. Then a brief review of the sort of the framework that I set up the last time, where I sort of isolated this abstract problem about clustering points in the plane into sort of small squares. That abstract problem, I'm going to attempt to give a detailed proof that that abstract problem is NP complete, and then depending on how much time is left at that point, go into less or more detail about how that becomes a proof that computing the parametric approximate rank itself is NP complete. So that's the plan. So let's start with a very brief recap of some of these definitions. So on this first board, I'm going to write down our parameters are some vector w, and I normally talk about w by its components, which are also vectors. So this is like a vector of vectors or something like that, which are a1 through to ah. These are the outgoing weight vectors for each of the h hidden units of the network. And then b1 through bh. These are the incoming weight vectors of each of the h hidden units. c1 through ch. These are the bias values for each of the h hidden units, and a single vector d captures the bias values for each of the output units. So these biases are individual; these are scalars, but I just bundle all of the output unit biases into one vector because I don't often need to refer to those individually. So this kind of parameter leads to a neural network function, which I'll call f of w, and it implements this function. There's a contribution from each of the h hidden units, and that contribution is the outgoing weight vector multiplied by the activated value of that unit, which is using the tanh activation function, the dot product of the incoming weight vector with the input values. So that's multiplying the inputs by the corresponding weights, and then add the scalar bias for that unit. And this, oh yeah, of course, after all of that, we have to add the the output unit's bias vector. And so this just reminds you of the notation that we're using. So let me see. Next, we have to talk about rank. The rank of W, we defined and studied algorithms in detail last time for computing this. The rank is of a particular parameter. Say that parameter is implemented with some number of hidden units, but maybe not all of those hidden units are strictly necessary to implement the same function. It could be done with fewer. And then that will come up in the rank. So the rank is the actually minimum number of h I need one more thing of notation here. This parameter space is called WH. I need the minimum number of hidden units such that you can implement the same function using some parameter in that parameter space with that number of units. So there has to exist a parameter that is in this sort of smaller architecture, or potentially smaller architecture, such that you get the same function. And we discussed last time how that, that equality there is equality of functions on all inputs, and some of the results might be a little bit different if you relax that constraint. Okay, and then finally, the parametric approximate rank. So we talked last time, most of last time was about this concept of the parametric approximate rank, which is an attempt to say, okay, in this case, you need to have found a parameter that implements exactly the same function. You might be interested in finding a, let me get this right. So this is saying you take your parameter and you say, what is the absolute minimum number of units that I need to implement the same function? But maybe you started with a parameter where you are using all of the units, but some of them you're not really using a lot. They're not really affecting the parameter a lot. And if you tweaked this parameter a little bit, if you perturbed it a little bit in the parameter space, maybe then its rank would drastically decrease, because you'd be able to sort of notice there was suddenly a lot of redundancy. What you're saying is that the parameter you started with itself, maybe it doesn't have very low rank, but it's quite close to a parameter that has a very low rank. That's the situation that we capture in this definition of parametric approximate rank, which is abbreviated as P rank or prank. There's going to be a tolerance parameter, epsilon, which is just a positive scalar, and the parametric approximate rank is you look in a neighborhood of the parameter and you find the rank of the minimum rank parameter in that neighborhood. So this is the min of the rank of the parameter, the nearby parameter, which I'll call u. And I'm talking about u such that the distance, well, u has to be in the original parameter space. Such that the L infinity distance to the parameter that we're measuring is less than or equal to epsilon. So this is the sort of basic definitions from the previous two parts of this series that will, and so the parametric approximate rank, which is an NP complete problem. So that's the brief review of these definitions. And next I'm going to define what it means to be NP complete. I'm going to define the problem of computing the parametric approximate rank, and then state the theorem that I want to prove, which is that computing the parametric approximate rank is NP complete. Are there any questions so far while I get started writing up these definitions? Okay. Actually, I said I'm going to talk about computing the parametric approximate rank, but actually, in the framework of theoretical computer science, it's a little bit easier to talk about decision problems which have a binary answer rather than computing the parametric approximate rank, which is itself a number. We can talk about the problem of bounding the parametric approximate rank by some arbitrary by some arbitrary number. So this is that problem. So given some neural network parameter in some parameter space with h units, some epsilon, which is our positive tolerance, and some maximum rank. A problem that you could be asked to solve is this decision problem. Is the parametric approximate rank at that radius with that parameter less than or equal to that maximum rank, maximum parametric approximate rank R? And so this is a yes or no question, and so that qualifies this problem that I've defined as a decision problem. So this is the problem that I'm going to be proving is NP complete. So I'll talk about what that means. Definition, NP complete. Let me see. So a problem, this is going to be in terms of a couple of other definitions, which I can clarify in a moment. A problem is NP complete if, I'll give this problem a name. I'll call it X. There's two conditions. First of all, X has to be in NP. If you're not familiar with theoretical computer science and computational complexity theory, I don't think there's really an effort made to distinguish between problem classes and adjectives that describe problems. So for example, NP is typically thought of as a set, and so I say the problem X is in NP, which means the is a member of this class of problems. Whereas for NP complete, I'm using that more as an adjective, so I say the problem is NP complete. I mean, it's basically the same kind of thing. I don't think it's really important to make that distinction as far as I understand. But anyway, so there has to have this special property of the problem. It has to be NP, which stands for nondeterministic polynomial, and I'll clarify that in a moment. And then also, for any problem in NP, so this is for all problems. I'm going to call the second problem Y. I need a formal way of saying that X is at least as hard as Y, and that makes this definition mean that NP complete problems are the hardest problems in the class NP. The way I'm going to say that is with the concept of a reduction, and this is going to be kind of the core of the proof, is this concept of a reduction. So I'll introduce some notation here. Just better make sure I get it the right way around, because this is easy to get the wrong way around. All of the problems in NP have to reduce to the problem that you're trying to prove. And I'm going to write that like this. Another way of thinking about it is, well, I'll get to the definition, but basically it means that if we have a problem, if we have an instance of problem Y and we have an algorithm for solving problem X, we can basically use that algorithm to solve the instance of problem Y. And in that way, the algorithm for problem X must be kind of doing the hard part of problem Y as well. And if it's doing that hard part for all of the problems in NP, then that problem must be kind of doing the hard part of NP itself. And that's a formal way of saying that it's as hard as the problems in NP get. So let me see if I can make this Yeah, I don't think it's necessary. I'm not exactly sure what the background of people here is in terms of computational complexity theory, but I have a lot more detail on this in the preliminary section of my thesis if you want a primer. I think for today, the most useful thing I could do is give a list of kind of what it is that I need to prove in basic terms, or in more basic terms than this. This is sort of a list of what I need to prove, but I could break down each of these things and tell you what it is I actually have to try and prove in order to establish each of these two things. So let me try and do that. So NP, non-deterministic polynomial. This is all algorithms that, one way of defining this class is, sorry, not algorithms. This is all problems that can be solved if you had a non-deterministic Turing machine, or a non-deterministic model of computation that's more or less equivalent to a Turing machine in terms of its power and speed. So you have this sort of superpower called non-determinism. And if you can solve the problem in polynomial time using that kind of computer, then that problem falls into this class. Non-determinism basically just means that you can make guesses in a way that if they can work out, they will work out. And it's not really a physical, we don't know how to build computers like this in the real world. So an easier way to think about this is as follows. It's NP is problems for which if the answer, so these are decision problems, like the one we have up here, where the answer is either yes or no. The correctness of a yes answer has to be verifiable in polynomial time on a regular computer, a deterministic computer. So that's much easier to understand, maybe. Decision problems for which, when the answer is yes, you can verify that with some algorithm that's deterministic and runs in polynomial time. Now you get a clue. Someone is able to try and prove this to you. So think of it like this. In the example of parametric approximate rank, it would have to be, is the parametric approximate rank of this parameter less than or equal to R? If it was indeed true, I would have to be able to come up with some way of convincing you in polynomial time that it is true, in a way that you can verify that you can believe me in a sort of in a correct way, using only polynomial deterministic resources. I don't know if saying it is helping. Maybe I should have planned a more kind of comprehensive introduction to stuff.
You're being very precise. Can you mentally simulate having one beer and then describe NP? Like, what is the looser version?
Okay. Well, it's this is how I'm going to prove it. It's basically you sort of have to say, can I you have to come up with an algorithm and a sort of a proof method as well. So what's called a certificate, which is sort of the proof. I think by example would probably be easier. I'm gonna abort what I'm doing here and come up with an example of the kind of. It's going to be useful because we need to talk about SAT anyway. So I'm going to use SAT as an example. Hopefully everyone's familiar with the satisfiability problem. I can't remember if I mentioned it in a previous session, but this is given a Boolean formula. Is it satisfiable? In other words, is there a satisfying assignment of truth values to the variables that makes the whole formula evaluate to true? So can you come up with some inputs that make this formula output true? Yes or no? Decision problem. NP complete. Proof. No, sorry, is NP proof. It's a lot trickier to prove that this is NP complete. I'm going to assume that later. The proof is you use a satisfying assignment. Let theta be a assignment of truth values to the variables of the formula. That makes the formula true. So it's a satisfying assignment. So one important point is that such an assignment exists only in the case that there's a yes answer, and it always exists if there is a yes answer. That this is sort of by definition of the problem. And so it's very clear that this is what I would call a sensible or a valid certificate. That is the theta. Because if I have this proof, it must be that the answer is yes, and yeah, that's if and only if there. That's the sort of validity of this certificate. Then there's the verifiability of the certificate. So I have this certificate. I need to be able to convince someone that the formula is satisfiable. So I give them the truth assignment, and then this certificate can be verified in polynomial time by evaluating the formula. Evaluate the formula on theta, and to verify that it is a satisfying assignment. So this step only takes polynomial time in the size of the formula, because you only have to kind of process each part of the formula once as you're working your way through the formula to get the answer. Evaluating a formula is easy to do on a deterministic machine. You don't have to do any guesswork to get the output of the formula if you know what the input should be. So so you can verify that it is indeed a yes answer if someone can produce this certificate. And if they can't produce the certificate, if it's impossible to produce a certificate, it must be because it's a no answer. So this is the defining property of NP, non-deterministic polynomial time. And this is, we're going to be trying to mimic this proof to prove that our problem is NP. Maybe I might as well do that straight up. There's no need to go on to talking about the completeness part and then come back to this. So we can just go ahead and prove that parametric approximate rank is NP. And after just talking about this example, it will be very similar. So let me move on to the next board and try and do a similar thing, but for parametric approximate rank. So you could call this one of the lemmas, because our eventual proof that we're going to need is going to need to prove that PAR is NP is in NP, and that all other problems in NP are reducible to parametric approximate rank. So this is one part of the main proof, and so I'm going to call it lemma 1. And the lemma is that parametric approximate rank, this problem of fitting a bound to the parametric approximate rank, is in NP. And the proof goes, we come up with a certificate. So I'm going to be a little bit more specific here. On the previous board, I didn't sort of introduce a variable to represent the instance or anything like that, but I was referring to the formula. In this case, the instance of PAR is some w, epsilon, and r. So let's just introduce those variables. W, epsilon, r, like they're introduced in the definition. So w is the parameter we're working with, epsilon is the radius, and r is the maximum rank. So for the certificate, we want to use this a little bit of a more sort of subtle object that we want to use than a truth assignment, but it's basically going to be a set of instructions for approximately merging and eliminating units until, well, it has to, it has to be sort of fit within this epsilon in terms of every approximate merging, and it has to end up with a nearby parameter that is at most rank r. So I'm going to attempt to quickly write that down. When I say approximately merging and eliminating, I'm kind of referring to last time, so I'll just quickly remind you. This idea of parametric approximate rank, how you can think about computing it. We spent a bit of time talking about this last time and looked at some examples. You can think of, for example, taking two units that have very similar incoming weight vectors and biases, and just perturbing each of the incoming weight vectors and biases so that they then match. So that the units now have the same incoming weight and bias vectors. And then those two units are going to contribute at most 1 unit to sort of the total count of the effective count of units that determines the rank of the parameter. And if those individual perturbations were sort of less than epsilon in every dimension, then you know that this parameter, you've sort of got a recipe for finding a nearby parameter that is reducible. So that's the kind of instructions I'm talking about. I'm talking about a list of sort of perturbations that are each within epsilon of kind of size, such that, you know, the final parameter that we get is no further away than epsilon in L infinity distance. I want this set of instructions to eliminate not just any number of units, it has to eliminate at least h minus r units, because then that will be possible only if the rank is at most r. So that's the certificate. I think you can see that it exists only if this nearby parameter exists, which is sort of the defining property of the decision being yes. It also exists if a nearby parameter exists, because based on the nearby parameter, you can sort of think, well, okay, which units would I have to move in which directions to get to that parameter? So, so this set of instructions is going to get you there. I guess to go back to the previous board, I told you the certificate has to exist if and only if the answer is yes. So hopefully you're satisfied that this kind of certificate is going to exist if and only if the answer is yes, the parametric approximate rank of this parameter is at most r. And it just remains to check if we can, given these kind of instructions, can we verify them in polynomial time? We can verify them in polynomial time. To verify the certificate, we just carry out the instructions.
you outline briefly why it's not possible that there's a nearby parameter that can't be reached by these recipes? Sorry, why that's impossible. So you wrote there that you use a set of instructions. I mean, you give the set of instructions that you can do it, but what's to stop there being a conspiracy where there's a very close by parameter that's just alien somehow and can't be reached by these operations?
I have to think about that for a moment. I think it's relatively straightforward to kind of come up with the instructions based on the nearby parameter. So, like I have somewhere, let me try and see if I find a written version of this that I can refer to.
I guess I'm asking the question because I'm not sure that's necessary. You said it out loud, but is it? It's not necessary actually to show it's in NP, right? I mean, you said you can have a certificate if and only if it's true, but it suffices to just have it be true if there's a certificate, no?
You want to verify all yes instances. So if there is some nearby parameter that that is somehow hard to describe, we would need there to be also some other nearby parameter that is less hard to describe or something like that.
No, but you don't. I mean, it's an inequality, not an equality. If PAR was an equality, then you would need that because you need it to be, you need to exclude the possibility of some nearby parameter that is lower rank than the thing you're trying to certify. But you're trying to certify an inequality, so isn't it sufficient to just have it be true if there's a certificate? You don't need the converse implication.
True if there's a certificate. But if the answer is yes to the decision problem, aren't you talking about a case where the answer is yes to the decision problem, but you can't come up with this kind of certificate? That would be a problem for the proof. Because the definition of NP is that you need to be able to verify that case as well, all yes cases. So the nearby parameter that has low rank, but it must be describable in this way, because you could just imagine taking that parameter and carrying out the reduction algorithm that we discussed in the first session. That algorithm tells you merge this unit with this unit, and then eliminate this unit, and then merge these units, and then eliminate this unit. Each of those operations becomes a step in your instructions that you use for the certificate. So you can build the certificate based on the reduction, the sort of execution of the reduction algorithm that we studied back then.
What if this nearby conspiracy parameter is already reduced? Why is it that this parameter W, when you run the reduction algorithm, will find that one? Maybe
right. Okay. One. Okay. It might be pseudo reduced. Like it might have a lot of 0 units, but that's not the same as reduced. So the reduction algorithm, if given a parameter that has a bunch of blank units where the input, output, and bias are all 0, the first step that reduction algorithm does will be to remove those units. So you just include that as an instruction.
Yeah, that seems also
it must be that if you're nearby to that parameter. Okay, go again then.
Well, maybe you're about to answer my question. Yeah, go ahead.
What was your question again?
So you're saying if you're nearby that parameter, then those particular entries must be sufficiently small that you would... Okay.
Exactly. You'd be able to approximately eliminate them.
Yeah, okay. Yeah, okay. Yeah, obviously there's details there, but I think that's a good high-level plausibility argument for the reverse implication. Yeah, thanks.
Cool. Okay, so yeah, I actually I have this whole thing worked out in a bit more detail than I wrote in the thesis. So if after reading, if anyone is reading this chapter and has still unsure about these questions and the details of the proof, I am prepared to defend them because I do have them worked out. Okay, so we need to verify this certificate now. So we have this sort of set of instructions that says which units to merge and which units to eliminate. It's important to sort of have that set of instructions is a polynomial object itself, so that following them, for example, if the instructions are very long and it takes exponential amount of time to just read them, that would be a problem. But each of these instructions is very simple because it's just sort of like merge these two units or eliminate this unit. And there can only be so many of those. In fact, you only need h minus r of those, and that's going to be polynomial in the size of the instance, which is sort of determined by the size of the parameter. So just follow the instructions is the first step, and carry out these merges or these eliminations. And without going into too many details, there's sort of obvious ways to do it. For example, if you have to merge a bunch of units together, they must all be, for this to kind of work, they must all be sort of close enough. So just pick some kind of centroid of the incoming weight vectors that you started with. Like, for example, if it's just two incoming weight vectors, just pick their mean, the mean of their weight vectors and bias, and use that as the new weight vector that you merge onto. Because so it's always possible to follow these instructions, and at the end of following the instructions, you'll have a parameter. And because each of the parameters, each of the instructions kind of corresponds to reducing the rank by 1 if the instructions are valid. You should be able to check that happened by computing the rank of that parameter. And computing the rank, we know, is a polynomial operation. We discussed an algorithm for that last time that ran in polynomial time. Several algorithms, actually, I think we discussed over the course of the last 2 sessions that would allow you to do this in polynomial time. And so then you just have to check check that it is less than or equal to r. So to summarize this proof, in the case where the instance is indeed it's a yes instance, so the parametric approximate rank is indeed less than or equal to r, it should be possible to construct this certificate based on some nearby parameter that has to exist that has a low rank. So you should be able to sort of inspect in which way that nearby parameter has low rank based on the algorithms, and then construct these simple instructions which serve as a compact polynomial length certificate. And then you give that certificate to a verifier who follows the instructions in polynomial time and then computes the rank in polynomial time of the resulting parameter and verifies it against the rank bound. In the case of a no instance, that means there is no parameter nearby that has rank less than or equal to r. And so it should be impossible to create this kind of certificate. The way of seeing that is to say that if there were these instructions, then that would produce a nearby parameter, so the contrapositive. So that's a proof that PAR is in NP. Any other questions about that one? All right, maybe let's do the much more intricate and interesting part, which is the reduction. So yeah, I think it's appropriate to maybe talk a little bit more about what this concept of a reduction is, what we're going for again, in terms of what I'm actually trying to prove. So in this case, for all problems y in NP, I have to somehow prove that x is at least as hard in some way that I haven't formally defined. The formal definition is using a polynomial amount of resources, any instance of the arbitrary NP problem can be transformed into an instance of PAR with the same answer, yes or no. So they're all decision problems, so they all have yes or no answer. They all have the same output type, but the inputs are quite different. For example, formulas, Boolean formulas versus neural network parameters and some other numbers. So for example, what we'd really like is to be able to prove things of the form SAT reduces to PAR. And what that would mean, let me just spell out this. With some polynomial algorithm, I can take a formula phi, which is an instance of SAT, and transform it into some W, epsilon, and R, which is an instance of PAR. Such that these instances are equivalent in that they both have the same answer. I can write it something like this. SAT of phi is yes if and only if PAR of W epsilon R is yes as well. So this thing would be the reduction from SAT to PAR. What I have to prove is not just that SAT goes to PAR. We know SAT is an NP problem. Also have to prove that any other problem in NP, the complexity class, also can be transformed into PAR. That's obviously a kind of Herculean endeavor to try and do that. But fortunately, a famous theorem from early in computational complexity theory is that SAT is actually NP complete. Not only is it NP. So we're going to use this theorem. It's called Cook's theorem or the Cook-Levin theorem. And that's SAT is NP complete. And so if we know that SAT is NP complete, what that means is that all problems, for all problems in NP, that problem reduces to SAT. This does a lot of the work for us because actually now all we need to do is show that SAT reduces to PAR, like in the example above. And this reduction is actually transitive because you can just compose the polynomial algorithms and you'll get a new polynomial algorithm. So if you combine this Cook-Levin theorem with a reduction from SAT to PAR, then we don't have to worry about all of the other problems because you could transform from any of those into an instance of PAR by first transforming into a SAT instance and then transforming that SAT instance into a PAR instance. Are you all happy with that? let's get to work proving then that SAT reduces to PAR. Actually, that's quite a complex thing. You know, we have these arbitrary Boolean formulas and we have these neural network parameters. Those things are quite different. And so this is where I'm going to introduce that that abstract problem as kind of a middle step, because it turns out it'll be simpler to think about working on an abstract problem compared to working on neural networks with their complicated parameters and input weight vectors, incoming weight vectors and biases and everything. So I'm actually going to do it like this. So we have, if you like, all problems in NP, which we know reduces to SAT. Other foundational work in theoretical computer science has shown that SAT itself reduces to some kind of more restricted versions of SAT. Which, for example, place certain restrictions on the instance. So, for example, it has to be in a certain logical form, using only and or connectives and negations, and it has to have all of the ands, the outermost layer sort of distributed out, and all of the ors on the inside, and negations on right on the variables. And there are only a certain number of variables that you can have per instance, per disjunction, and various restrictions that I'm going to go over in a moment. It remains NP complete. So you can take an arbitrary formula and find an equivalent formula that has these restrictions. Some restricted variant of SAT. In my thesis, I actually find some extra restrictions. I'm not 100% sure that these are novel restrictions, but they are sort of tailored to my use case. I call this variant XSAT, X for further restrictions. So I do this reduction in an early chapter. The one I'm going to show today is that you can reduce XSAT to a problem called uniform point partition. And the one I sketched last time is that you can reduce uniform point partition to PAR. So, and if we get time today, we can talk about that as well. But we'll focus on this one. So here we have Cook-Levin up here, and then various other foundational results in theoretical computer science. And then I have a minor extension of those where I just get exactly the restrictions that make the instances so simple that I can sort of easily build networks of points out of them. And then we finally transform from logic into sort of the Cartesian plane, and we convert between these formulas and sets of points. But we're focusing on this abstract point partitioning problem and not on the neural networks. The step that connects it to the neural networks is, I gave a little bit of an overview last time about how we translate these points into the positive quadrant, and then partitioning is sort of the only way that you can have reductions and stuff like that. So I want to focus on this blue part next, which means I'm going to have to introduce XSAT and UPP. So I'll try and do that briefly. But any questions about this this logical structure of the theorem? All right. So so I want to introduce XSAT. This is a restricted variant of SAT. And I'm not going to prove that it's NP complete, or that it is NP and that it can be you can reduce sat itself to it, but that proof is in chapter 3. Section 3.4 has this proof in my thesis. This is a problem of the instance is given some Boolean formula in conjunctive normal form. And what that means is it has this kind of form. It has some variables. V is going to be a bad letter if I want to use that for or. Let's use a capital X to be our variables. X1 or X2 or X3, for example. So these are disjuncts connected in conjunction with other disjuncts, X1 or X4, for example. And we keep going. It has maybe many of these. And actually, some of the variables might be negated. They don't all have to be positive like this. So we could have some of these be negated variables. There's going to be a couple of other restrictions. So C and F is the first restriction. It sort of means that you have to have these disjunctions on the inside of your conjunctions, and there are no other different types of logical connectives at play. But there are also some other restrictions. First of all, there's some restrictions on the number of variables that you can have per clause. So for example, here we have a clause that has 3 variables, and here we have a clause that has 2, and they are the only allowed possibilities. Each clause has 2 variables or 3 variables. So no more, no less than 2 or 3. That's the first restriction. The next restriction is that, let me just find my list to make sure I'm getting this exactly right. The variables themselves, so the clauses have at most 3 variables. The variables also have at most 2 or 3 occurrences. So each variable appears, the number of clauses it appears in is restricted. In 2 clauses or in 3 clauses. And again, no more, no less. In addition to that, at least one of the occurrences of the variable is negative, so is negated. So for example, if we have a look up in the example here, we've got a non-negated version of x1 here and a non-negated version of x1 here. Because of this exactly one negated condition, out here somewhere there must be some other occurrence of x1 and it must be negated. Here we have x2 occurring once negated. It has to occur 2 or 3 times. So in some other clauses, it must occur, and it must occur positive because it's already occurred negated. It has to be at least once. It could be in 2 other clauses out here. Same for x3 and x4. Maybe it's going to occur again. It has to occur again at least once negated, and maybe it's also going to occur again as just x4 without negation. So these are sort of some restrictions on the number of variables per clause and clauses per variable. The final restriction, you can actually think of these as restrictions on some kind of graph of the formula. If you have sort of some nodes representing clauses and some nodes representing variables, and a line between them that represents that the variable occurs in that clause, we've basically said that this graph is going to have a very restricted degree on its nodes. All of the nodes are going to have either degree 2 or degree 3. Also, if you were to give some of these edges a sign, there's going to be structure to that as well. The final constraint is a restriction that is best phrased in terms of the graph itself, and that is that this graph, if you built it, is going to be a planar graph. The variable clause graph is planar. So most of the work in proving that these restrictions don't restrict the class of formulas too much, that there are still hard formulas in this class. Most of that work has been done by prior work, and I was really just putting a few of these things together to get exactly these restrictions, because having these restrictions on the graph is going to vastly simplify the number of different possible types of formulas we have to consider when it comes to turning these graphs actually, or these formulas, into sets of points. It's very helpful to have planarity, because it means we can basically lay out the graphs on the plane. And it's very helpful to have restrictions on the degree, because it means we can use a grid, for example, to lay out everything in a rectilinear manner. And it also means it's very important, or it's very useful to have restriction of everything to 2 or 3 as the degree, because there are only so many combinations then you can have for each node in terms of the number of directions that different edges go in. And put together, it means that there's only a handful of cases that we have to consider when it comes to converting these formulas into sets of points. So I'm going to be referring back to each of these conditions throughout the proof. Let me now introduce the abstract problem that we sort of built up last time, but I'll formalize it now. And this is uniform point partition. First, I need a definition, which is of a K epsilon partition. Just going to find this in my thesis as well, so I make sure I don't miss anything in the definition. So let's say we have some points. This is another, basically this definition is going to be kind of like satisfying assignment. So the set of points is going to be, the decision problem is going to be about whether or not this kind of partition exists. But to define the partition itself, we have to start with a set of points, just some finite number of points in the plane. Keep everything simple. We're working in the plane because we don't need anything else, and we have planar graphs, so it's going to work out well. And also K and epsilon are kind of parameters here. A K epsilon partition is a way of grouping the points into at most K groups yeah, let me write it like this. So it's a partition into K sets, but I guess it's a bit weird to call it a partition because some of these sets are allowed to be empty. They're just not allowed to overlap. Each of these is a subset of the indices 1 through n. So you can think of this as a way of grouping the points, the n points, into K groups. And I'm using the word partition because they're not allowed to overlap. So any point can be in, has to be in exactly one group. But actually, partitions, I'm not sure if you would normally allow partitions, any of the cells of the partition to be empty. So that's a bit of a quirk of this definition. We're going to allow that. But you can think of it as a partition if you say it's at most k groups. Okay, anyway, so then there's a constraint, which is the epsilon, which is that each of these groups of points has to kind of fit inside a small square, which has width epsilon. Such that the uniform distance, or the L infinity distance in any, the maximum such distance in any group, which you could call like a diameter of the group or something like that, the L infinity distance between points in the same group, any 2 points in any group, is at most epsilon. So the example is, just really quickly, you could take these points, and if you have a radius that's enough to, or a diameter epsilon that's enough to fit these ones, but maybe this one has to be in its own group, or you could perhaps decide to partition them slightly differently if say, the distance is worked out that you could fit these two together. These kind of things. So if this is epsilon, these would be examples of 3 epsilon partitions. Now the question, the computational problem of this is whether or not such a partition exists. If you have a set of points and a particular k and epsilon, can you do it? Can you cover all of those points with that number of squares? So this is another problem. This is the uniform point partition problem, which is the one that I've called UPP. And it's the abstract problem that I'm going to prove is NP complete. So you're given your points, n of them in the plane, and also you're given k, and you're given epsilon. And the question is there a k epsilon partition? Of the points. So that concludes the definition of these problems. It remains to show that there's some way to convert any of these restricted satisfiability instances, where, remember about satisfiability, it's the same definition. I guess I didn't actually finish this definition on the previous board, actually. I just told you about the instances. But the question at the end, the computational question is the same. Is there a satisfying assignment? Just like SAT. That's why I called it a restricted variant of it. So remembering that a reduction is a way of converting instances of this initial problem, in this case XSAT, to instances of the new problem, in this case UPP, in a way that the answer is the same. I have to be able to transform instances of restricted satisfiability, so these very constrained instances, into sets of points and some k and some epsilon, such that there's a k epsilon partition if and only if the original formula was satisfiable. So suddenly satisfying assignments have to correspond to k epsilon partitions in some way. And so that's the task of the proof, is to set up that correspondence in a way that can also be, that transformation has to be polynomial.
I suppose in principle it might be possible to prove that a satisfying assignment exists if and only if a partition exists without actually having a correspondence in any sensible way, right? Are there any reductions you're familiar with in the complexity literature that look like that? I mean, usually, of course, you would just construct an instance from an instance, but...
Maybe I haven't been careful about the way that I've been saying things, but the task is there has to be a polynomially computable instance, and that gives you a correspondence, right? Well, maybe it's at
least a map.
Yeah, it doesn't have to be a bijection or anything like that. You can map multiple instances to the same instances. You don't have to map to all instances.
In fact, you wouldn't. I mean, most of the PAR, in some sense, most of the PAR problems are kind of trivial, right? You could take epsilon to be extremely large, or R to be extremely large, or something. So it's only a very limited set of PAR problems are in the image of this translation.
That's exactly right. Yeah. In fact, we're not even stepping out of the plane during this reduction. So anything where there's more than one input unit is never going to be in the image of this particular. Although you could design another reduction that used those dimensions. We won't. So yeah, it's not a bijection. And so if you're kind of reading into that when I said correspondence, I guess. They correspond only up to the sort of binary yes or no-ness or something like that, which is not very much. Okay, let's do it. This is the fun part where we sort of are turning formulas into sets of points. So yeah, let's go to the next boards, I guess. Or would it be useful to stand near these boards? I could get rid of some of the early boards in this set.
No, I think we can start on a new set.
All right. Okay, so let's do it. So I'll give you an overview of the reduction. I already sort of mentioned that we're going to be laying out planar grid, planar, a sort of graph version of the formula. We're going to be laying it out as a grid in the plane, and then we're going to be the details consist in sort of how you lay it out in the plane and how you transform the grid that is laid out into the plane into a set of points, such that the partition exists if and only if the graph that you started with corresponded to a satisfiable formula. So it would be very helpful, I think, to have some running examples. And so I'm going to spend a moment to come up with an example instance of the XSAT, just a really simple one. It's actually a little bit tricky. You need a few variables and clauses to get something that's unsatisfiable. So I'm just going to start with one that's sort of quite easily satisfiable. And that is going to be the following. So let's call this by 2, and it's going to be 2, and I'm not going to do 1 and 3, which are the examples in my thesis, but I'm still going to call this 2 instead of 1 or 5 or something, because then it's consistent with the examples in the thesis. But I am going to make a change in that. Oh no, okay, I'll do it like this. So I'll just do my V's so you can distinguish them from ORs. I've already screwed this up. It's going to be not V1 or V2, and V1 or V2 or V3. Let me just write this out actually and then figure out the negations. V2, V3. So that's negated. And so is that. I was using a prefix for negation earlier. I've just switched to this bar because it's going to make it a little bit more compact. Now, okay, I want to think of this as not a formula, but as a graph. And I should, in the meantime, sort of show you that it's a planar graph. I have three clauses. I have three variables. Let me draw them like this, I think. It's going to make it easy. So we'll make this V1, V2, and V3. We're going to have some clauses, which I'm going to use as open squares, and variable nodes are going to be these colored circles. So V1 occurs in the first two clauses. Oh yeah, these clauses are in the same order as at the top. I'm not going to label them. We have a positive edge here. Sorry, that's actually a negative edge. And this would be a positive edge because V1 occurs positively here and negatively in that first clause. All right, V2 is in all three of the clauses, and it's negative in the last one and positive in the other two. And V3 is in negative in the second clause and positive in the third clause. So we could run through each of the checks on the for restricted xsat to show that this is actually an instance of the restricted satisfiability problem. So let me see. So this is clearly a planar graph. The way that I've drawn it is a proof of that. The clauses all have 2 or 3 variables. That's easy to see in the top rendering. And also the degree of each of the clause nodes is 2 or 3 in the graph version. And the variables, it's easier to see in the graph version, all have degree 2 or 3. So they all have 2 or 3 occurrences in various clauses. And they all have exactly 1 negative occurrence. And that's also easy to see in the graph. So this formula is satisfiable. It's pretty easy to come up with satisfying assignments because they're so free. We can just use V1 and V3 to satisfy these clauses, and then V2 to satisfy the middle one. So when we transform this into a set of points, it should be a set of points that we can partition in some way that we set up. There's another example in my thesis that has 5 clauses and maybe 6 variables or so. And that one is unsatisfiable. And that's actually the smallest unsatisfiable one I could. No, sorry, it's phi1 is the unsatisfiable one. It has 5 clauses and 4 variables. And it's the smallest unsatisfiable restricted formula that I could come up with, but there may be some smaller ones. Anyway, so our job is going to be to turn this graph into a set of points. The first step is going to be to do what I said earlier, to transform it into a grid format, a rectilinear format. So I'm going to move on to the next board. Now, I'm going to sort of use this example to kind of, instead of writing up all the details on the board, I'm going to be drawing this example. But I will talk about how you can always do this. So because these graphs are planar and have degree at most 3, there are some algorithms that were studied by sort of graph theorists and engineers in the 80s for transforming these kind of graphs into a planar rectilinear layout. For example, this has applications in circuit design. In our case, we can use any of these algorithms. They all run in polynomial time, and they will transform this kind of graph into a layout that might look something like this. So I guess it would be useful to label the clauses because they're going to move around a little bit now. So let's just call them C1, C2, and C3. And then here we go, C1, C2, C3. I want a rectilinear grid. I want a rectilinear integer grid. So you could do it something like this. So imagine some sort of evenly spaced nodes, and the edges between them are, I want this to be an interesting example. I'm going to make it not as minimal as it could be. this will do nicely, I think. It's not really evenly spaced. So this is meant to be some kind of integer grid. So you can imagine that these elements are evenly spaced on an integer grid. And the fact that it's possible to do this on a polynomial size grid in polynomial time is proved in some papers that I cite in this section of my thesis. And it relies on the fact that the degree is at most 3, and that the graph you started with is planar to begin with. So we're using some of those restrictions for this to be possible. Anyway, once we've got this grid layout, basically, now we're ready to sort of mechanically translate this into a set of points. The way we're going to do that is by taking each kind of each intersection, each node of the underlying integer grid, rather than each node of the graph. So I'm talking about, for example, this point, this point, this point, all of the nodes of the grid. And I'm going to transform those into a set of points that form some kind of interlocking tiles. And the tiles are going to then make up, these are meant to be kind of evenly sized, but I'm already screwing that up. Anyway, I think you can see what I mean. These tiles are going to be sort of chunks of the plane. We could scale this to whatever scale we want. Let's just pretend that these are like unit squares or something like that. The key to this reduction, this algorithm that is transforming these graphs into points, is that we're going to treat each of the tiles. We're going to have a recipe for transforming each possible tile that we could have. So there are a bunch of possible tiles. For example, we've got tiles that look like this, where we have a clause and it has 2 edges. But there are some other possibilities, like for example, over in the other corner, you can see an example where the clause is like this, but this is really just a rotated and reflected, or a rotated or reflected version of the other one. So actually, we're just going to focus on this one. We have another example involving a clause down the bottom that looks like this. You can imagine that there would be some other possible rotations of that. There is another example that we might have, we don't have in this example, but we might have involving a clause that would look like this, or a rotated version of this where the lines were going up and down instead of left and right. But actually, these three are the only, up to rotations and reflections, these three are the only types of clause tiles that we could get. What other tiles do we have? How about this one here? This is a sort of edge segment that doesn't involve a node or a variable or clause node in the graph. There are 2 of those that we should worry about, up to rotations and reflections. And they look like this and this. And now there are some variables. Actually, I haven't drawn the full graph, have I? Because I forgot the signs, but we're going to move all the signs to the variables. So I haven't screwed anything up yet. So I think it's plus, plus, minus, minus, plus, minus, plus. So the signs, I can write them like this: plus, plus, minus, minus, plus, minus, plus. And probably that's right. Otherwise, I might have subtly changed the formula, but we'll figure it out later. So there are a few more possibilities, because in this case, we have to care about the orientation of the negative edge for the variable tiles. But there's not that many to worry about. I think there's 4 possibilities up to rotations and reflections. And they look like these. We could have sort of this plus minus and variable on a corner. If you reflect that diagonally, you can get the minus on the other side, and then you can do all the rotation, so that's no problem. We could also, of course, have the plus and the minus going up and down, or left and right. They could have degree 3. So then there's only one possibility of degree 3, but when you allow for the sign, the negative could be here, going up, that is, or it could be going sideways. And the positives will be the other two.
Can I just clarify something? So both SAT and the restricted planar SAT and these other restrictions, they're all equivalent somehow, so they're all NP complete. And the role of planarity the role of planarity here is to make it easier for Matt to think about when he's proving it, and easy to communicate with pictures, and that's about it, right?
Yeah, well, that's right. It's sort of simplifying the proof, because if, for example, let's say I had made the restriction on the original, on the XSAT instance that we started with, made it that you could have degree 4 instead of degree 3 in the graph. Or that you could have non-planar graphs, so that when you do this grid layout, you might have some crossing edges. Then I could actually still probably do the reduction, like come up with points for those types of tiles that you would get at this stage. Like, for example, a tile that has a clause with 4 edges going away, or a tile that has a clause, sorry, no clause, just 2 crossing edges that are understood to be like this, or maybe another one that was sort of like this and like that. There's more possibilities to consider. If you're allowed to have degree more than 4, then you could probably come up with some way to like embed a clause into multiple tiles, and you could have the clause look something like this, and then you can support up to degree more 8. So you could come up with point arrangements for all of these things. But yeah, so I basically said I simplified the XSAT instance as much as possible to make this step as easy as possible. And this is very common in theoretical computer science. In computational complexity theory, people will sort of study variants of problems. Sometimes you make a restriction on the instances, and it turns out that the remaining instances actually you can solve in polynomial time. And so they're not NP complete unless P equals NP. For example, if you had restricted the degree to 2 of the clauses, then you have 2SAT, which is polynomial time solvable. So it's kind of a fine line when you make these restrictions. But in terms of SAT, there's this long history of studying lots of variants that people study where you make some change and it's still NP complete. In the case of planarity, I can tell you what this proof kind of looks like. For example, you have to reduce an arbitrary graph of a formula basically to a planar graph, and it might seem like that is like some really hard thing to do, but there's a paper from I think the I can't remember if it's the 80s or the 90s, but around then. But back on this board with the graph for a moment, just for this sidebar. You set up the graph of the formula. It looks something like this. You've got your clauses up on one side. You've got your variables here, and you set them up. They look, sorry. This graph would, I guess, look something like this. Variable 2 goes to all 3, and variable 3 goes to the last 2 clauses. Okay, this graph happens to be planar, but in this particular layout, it's got crossings. You can imagine also there would be non-planar graphs that you could lay out like this. You zoom in on these intersections, and you introduce some intricate connection of new clauses and variables that that preserves the logical value of the formula, but changes it to a planar graph because you've removed the intersection. I can't remember exactly, but it's this very intricate like mess of variables that you put in here, but it's planar. And so you may be expanding the size of the formula by introducing auxiliary variables, but you're doing it in a way that removes these crossovers. Basically, from like a, I don't know, from like a proof perspective, you could do that before or after you sort of make the transition to the plane, like in points in the plane, right? I could basically start with a non-planar graph, and I could deal with the crossovers in the plane by coming up with points that you can partition in some way such that you kind of do this crossover. Or I could observe that that restriction also doesn't, you can do that reduction in the, you can do that transformation as like a pre-processing step on the satisfiable, on the satisfiability instance. Well, first of all, because that particular observation has already been made in the literature. But in my case, I also added a few extra restrictions in my thesis to XSAT. That's going to then make the other proof simpler. So that's the kind of, that's the story of what's going on here. I will note that the only additional restrictions that I introduce, so a lot of the restrictions of XSAT are, I have a citation for where that's established in the literature, but I wanted to ensure that you have not only at most 3, but at least 2 degree for each of these things. So I had to figure out how to transform away the cases where you have 1 or 0 occurrences of a variable and the cases where you have a clause with 1 or 0 variables in it. But intuitively, those cases are not super interesting. If you think about the satisfiability of a formula where you have a clause that has, well, a clause that has no variables, if you allow that kind of thing, it's conventionally defined to be false in any assignment. And so you have kind of a trivial instance in that case. So you can that's kind of like an edge case that I'm just smoothing out before I make the transition to the points, so I don't have to deal with it. The number of negatives is another one. This one is really clear to see how you could do it before or after. So, okay, so if I look here on the graph, not the grid graph, the original graph with the formula instance, have a look at this. If this had have been a variable that has all positive occurrences, that's another kind of like trivial case where you just set that variable to true and it can't harm you in your attempt to satisfy the formula. So you can reason through like pruning those cases from the formula. But it could have been 2 negatives and a positive. In that case, when it comes to sort of arranging these tiles or sort of arranging the partitioning, it's just sort of like about the orientation of the variable. Do you consider true to be sort of going in this direction, or true to be going in this direction? So you're kind of just reversing the variable. It made a little bit more sense to me to do that at the logical stage, because basically, as it turns out, I would be using basically the same set of points in each case when it comes down to this tile. And that is because this kind of has the same logical content, those 2 variants of the formula, one where it's negative, negative, positive, and the other where it's positive, positive, negative. So I kind of observed those kind of similarities when I was constructing the point sets. And I was like, well, hang on a second. This is like one of those without loss of generality. I'll consider this case or something like that. Cool. Okay. So it's just hit 5:30. I would be happy to kind of pause. This is obviously going to take, we're just getting into sort of the meat of it now. If you guys want, I'd be happy to pause and we could resume this another time. Otherwise, I'm free, so I'm happy to push on for a little longer and try and be a little bit more succinct in my description of basically what remains is to describe for these 9 tiles, describe the point set that I'm going to place inside these unit squares instead of the graph, and then convince you that the resulting set of points that I build will be will be coverable, will be partitionable if and only if the formula was satisfiable.
I think I'm going to make
what do you guys think?
I think I'll make an executive decision and say that given we have a talk scheduled for next week already, it would be good to finish this in 2022. So if you're free, I think we should do that.
All right, let's do it. Okay, I'll try and be fast without rushing it. I'll just try and be a little bit more efficient, I guess. Okay, so point sets. Okay, the idea of the points, I have to show you the idea of like how we're going to partition, how we're going to think about this thing being partitionable or not partitionable. The key idea is that you can kind of communicate binary information through a point set by having points that are spaced epsilon apart. So on this next board, I'm drawing a line of points. And I'm going to say these are spaced epsilon apart such that we get to decide epsilon, we get to decide the scale because we're building the instance, and epsilon is one of the parameters of the instance. But so yeah, we can just set this to whatever we like, but so we'll just think of it as epsilon for now. You can choose to partition this set of points in kind of two ways if you restrict the number of cells that you're allowed to use. One of them could be like this, but then you won't get this point at the end. Another way would be like this. And then you won't get this point at the end. So if you only have 4 groups to play with, you kind of make a binary decision about which point to exclude. You can communicate that decision along a chain of points like this. That's the key kind of mechanism that I use to establish the relationship between satisfiability and the partitionability of the points. I'm gonna set up these variable sets of points for the variable tiles. So say, for example, if you have a tile that looks like this, so a variable where up is positive and down is negative, I'm going to come up with a point set. Okay, I'm going to make the scale 1/4, and this is a 1×1 square. So this is just a sort of zoomed in version of that tile. I'm going to put some points down like this. One in the middle here, one here, and one here. And actually, I guess, yeah, I'll put some points on the border here that are going to be overlapping with the neighboring tiles. And I'm going to allocate, for this tile, I'm going to allocate in the final number of partition cells that I allow, the k. Because of this tile, I'm going to allow 2 cells. And when it comes down to it, we're going to have a choice of partitioning this tile's points, either like this, so that the upwards point gets included and the downwards point gets excluded, or like this, so it's the other way around. I haven't drawn that very well, but so the upwards point is excluded and the downwards point is included. So that's where the binary decision is going to begin. I'm going to associate the point being excluded or excluded. I'm going to associate that with the assignment of value to the variable. I'm going to use these sequences of points like this to implement the wire tiles. Like on each of the wire tiles, I'm going to have like a segment of that sequence of points, and you can see how it can go around corners here. And I'm going to communicate that decision that happened at the very tile all the way to the clause tile. And then at the clause tile, I'll make it so that you have enough partitions. Let me do an extended example. You have enough groups in your partition that you're allowed to use so that you can cover these points in the tile only if one of the variables was assigned in a way that was going to satisfy the clause. So I'm going to do an extended example here where we translate a section of the graph that might look like this. We have a clause that might have two other variables occur in it. We have a variable that was this one that I just drew, and we have two edge segments. I am going to need these kind of guidelines, so I'll quickly put those in. Oops. I'm just drawing the bits that it turns out I'm going to need. I think I'll need all of these. So I'm going to show you how a decision made at this variable tile can lead to the clause tile being partitionable or not. So for the corner wire tile, I'm going to use this arrangement of points. For the edge, for the straight wire tile, I'm going to use just another 3 points like this. And let me see. For the clause, okay, it's going to look like this. So, I'm going to communicate the fact that this variable, let's say this was a positive occurrence. Well, yeah, it's a positive occurrence. So if I assign this variable in sort of an upwards direction to correspond to true, then I want to be able to communicate. Well, what that will look like is like this. This top point on the boundary will be included. I want to communicate that all the way to this point being included, and I want to mean that it then, because this point is included, it then becomes possible to cover the points inside this tile. But if the variable was set to false, which is sort of a downwards configuration, like this, then if I use the same number of partition groups, I'm only going to get to here, and I'm not going to get to cover this point with those groups. And then this clause is going to have to sort of, I'm going to make it so that it has to be covered, one of these other points has to be covered for us to manage to cover all of these points. This is the basic idea. So I'll just show you that it sort of, the counting adds up. And it looks like this. So like I said, this brings us exactly to be able to cover this boundary point when it's true. And you can then see that if I use the other configuration for the variable tile, it would be going the other way. Sorry, it wouldn't make it here. It would, this would be going the other way, and we'd make it to here instead of including that boundary, that point on the boundary. So let me see. I have to be a little bit careful, because basically when you're doing this kind of reduction, I don't want there to be some other way of partitioning the points that I haven't thought of that sort of ruins one of the directions of my proof. But the beautiful thing about this kind of arrangement of points is that the wires, for example, are so simple. And what we're going to do is constrain the number of points really precisely. Sorry, the number of groups and points really precisely. So for example, for each of these wire tiles, we're going to have k plus equals 2, k plus equals 2. And for this variable tile also, k plus equals 2. And so the total number of partition groups that we have allocated based on these three tiles is going to be 6. So if we tried to use any more than 6 tiles, for example, you can imagine some deviant partition going like this at first, but then spending a whole square to cover this point, and then going like this, and going like this. and we somehow don't get to cover this point, even though we have the variable in the true configuration with our 6. No, sorry, I wanted to show a different example where I covered the point even though I wasn't supposed to, but this also is something we want to avoid. This is going to sort of make it impossible, but some other, when we talk about the existence of a partition, we won't prefer this partition. All that matters is that there's another one out there that does the right thing. Let me try and show you another example. Let's say we want to set this variable to false, but we still want to cover this point. So we could do so if we allocate more than the sort of fair share of groups. Here's the 6. If we add a 7th that covers this point, we've kind of violated this kind of sensible relationship between the direction of the variable and whether or not this point ends up being covered. But what that means is some other tile out there, we're going to have spent one of their points, one of their groups that was allocated to them. And the whole budget for these groups is going to be so tightly controlled that means that we're not going to be able to cover those tiles' points at all. For example, if you have a look at any of these tiles, the wire tiles, for example, the edge tiles, sorry, I should say, that look like this, and have k equals 2, if you have these points, even not including these boundary points, because potentially they could be covered by the neighboring tiles. But look at just these interior points here. If you only have a single group, it's impossible to cover all 3 because they're too far apart. You can only get at most 2 of them. If you're not clever, then you could get one of them. But the point is you can't get all 3 of them. So these budgets are going to be kind of tightly chosen so that it forces you to follow this sort of pattern that I was describing, where if the variable is set to true, it has to be that this point at the other end is going to be covered. And if the clause is going to be covered, with all of the points are going to be included in some group, it's going to have to be that the variable was set to true because we need this point to be covered as well. So yeah, I'm not sure exactly what to go into next. This is like the overview of the ideas of the proof, and there's a lot of details, right? Because for each of these 9 tile types, because then you can rotate them and then you can build any of these graphs for any formula. There's a set of points, and there's like some reasoning about the fact that you can or can't cover it with a certain number of these squares. And there's a detailed proof that you can't do it. You can do it if the formula is satisfiable, and you can't do it if the formula is unsatisfiable. I think the easiest thing will probably be to just set up the whole example that I have given here, the running example, as a whole set of points to show you sort of some of the points, the ones that actually come up in this example, and then partition it according to a recipe that I would try to argue is something universal. So you'll always be able to do this partitioning, and that will show you the ideas of the proof kind of in action in one of the directions, which is if there is a satisfying assignment, then there is a k epsilon partition. That's probably all we'll have time for, though.
I second that idea. That's when I was convinced, when I did exactly that.
Cool. All right. So I've set up a slightly different graph here to show you some more sort of edges going on, because the grid layout I used in my thesis was a little bit boring for this example. So it's a small formula, but it also gives you a small grid layout if you sort of remove some of these redundant edges. So I've added some. So I'm just going to have to look closely at this as I translate it. So we've got a 3x4 grid. So I'll attempt to put the type of tile in the top corner of each of these. Here we have a clause, and then an edge, and a plus plus minus variable, and then a clause. And a plus plus minus variable, and then a clause. We've already seen that edges look like this, for example. And I don't think I showed you this kind of variable, but I can quickly show you this kind of clause. It actually looks just like a corner edge. It turns out that a lot of these A2 nodes look sort of exactly the same, which is just, it actually has an interesting meaning logically. If you have a clause with just two variables in it, then if you set one of the variables, that has sort of a direct implication on the other variable. So it's like some kind of implication. So and you could take wires, edges, for example, and you could sort of replace them by a chain of implications through auxiliary variables. And it's all kind of the same thing. So that's one reason why variables, that's why clauses that have two variables look the same as edges in this construction. Also, variables that only have two occurrences, which I'm about to show you down here, this goes edge and then variable with minus and plus. This edge is just going to be a rotation of the other one, so straight down. And this variable is just going to be the same diagonal construction. A variable that has only two occurrences has a similar kind of function. If it's going to, well, because one of them is negative, you sort of pick which clause it's going to be satisfying, or not necessarily satisfying, because it depends on. Oh no, yeah, it's either you make it false and then it satisfies the one that it's negatively occurring in, or you make it true and then it satisfies the one that it is positively occurring in.
Can I just double check something? So the signs, the minus and the plus, they don't affect the position of the points or their spacing or anything. They just affect the mapping. They do from
actually. They do affect it in the case of this one, but not in the case of the degree 2 variable. It just happens that is the case. So what have we got here? This must be up, and then we have another minus plus variable. All right, great. Yeah, so I will show you the other three variable, because I guess it's kind of interesting. The variable's kind of interesting. This was a minus plus variable. Okay, so some of these we can fill in straight away. We have our diagonal construction for these corner wires, corner edges. Okay, and this is just doing the easy ones, and then I'm going to refer to my notes for the subtler ones. So this is sort of set up some kind of network, and the interesting thing that happens in these, like the interesting part of these formulas, is always the ones with degree 3. Although I guess sometimes the networks of things with degree 2 are themselves interesting. Okay, so this clause, we already saw. This looks like this. This was in the other example, but upside down or sideways or something. Upside down, I think. So the last one to do is this variable. So let me just refer to my notes on the variable. My box got a little bit stuck there, but it's back now. Refer to my notes on this variable. Okay, it's a kind of V-shaped formation here because the no, the negative goes to one side. So it's this kind of pentagon pointing towards the negative edge. So this one is not symmetrical. And if you changed where the minus was, the point set would look a little bit different. I'm thinking of this as like an arrow pointing towards the negative direction. Okay. So the thing about this variable, this is a little bit different from the other ones. The two degree variable that I showed you on the other example, it's using this parity of the partitioning of the sequence of points, like a linear sequence of points. But now we have what's more like a bit of a circle of points. And what we want is that we can cover like this, or we can cover like this, and not like that, but not sort of a combination of both. Because we talked about how we want to communicate using the parity of the sequences leading to the clauses along the edge sequences of points, the edge tiles. We want to communicate the kind of parity of whether or not you're covering the sort of point that leads to the next tile. So this set of points is designed so that if, for example, you choose to cover this, oh yeah, I should say that what the allocation for each tile is. And it's pretty simple because it's just 3 for each of these ones and 2 for all of the rest, I think. So if you're going to use 3 points in that tile up there, 3 groups in that tile up there, and you want to include this point on the boundary, you might as well include this point as well because it's nearby. But now you have to get these ones. So you better use the other 2 to get those. And you can't reach these. Well, I mean, it's not clear here because it's a little bit messy. But if you look at in the thesis, I've got like a detailed grid layout with like the guidelines and to the scale of epsilon. You can't reach to cover these points and also those boundary points. But then if you decide that you don't want to cover this point, then you have your options open to you. You can choose to cover this point. You can also choose to cover this one. And then you can just reach to do these 2 with the third. So it's like a choice of whether or not to put these 2 together or put these 2 together. And as you slide that, it then determines what you can do with the other 2. You can then slide these out to cover these. Or you can slide those in, and then you can slide out and cover the negative boundary point. So that's sort of the design behind this. For the other possibility of the variable tile with degree 3, I'll go back to this this previous board. If we're talking about something like this, the other possibility being the negative edge being in the center of the 2 positive edges. In this case, I used a slightly different construction. We've got these points for the boundaries. It's also k plus equals 3. But this time I'm going to use a v pointing towards the boundary in a way that if I choose to cover that, I need to get these ones in groups. But if I choose to not cover that downwards one, I can then cover these ones, and then I'm free to slide these boxes out to cover those boundary points. That's the idea here. These are a little bit weird because like you're kind of sliding the boxes around, and they kind of you have this sort of subtle mechanism. And I did spend quite a lot of time finding such simple sets of points that did the job. A much simpler way to think about what the variables are kind of fundamentally doing is to think about a cycle of points. So I'll just briefly show you what I mean. Maybe on a bit of a smaller scale, you can imagine if you had some kind of cycle of points here, and then in between certain ones, you had your boundary points coming out, I don't know, there and there, say. Make it that, with the same kind of parity idea, you can either combine these ones and these ones and these ones and go all the way around the circle. And if you do it like that, then maybe it's set up so that this is within space, but this one is not. You can't reach that second boundary point. Or you could choose to shift the way that you're pairing things together in the cycle by 1, and then you wouldn't be able to reach that first boundary point, but you would be able to reach the second one. So you can kind of rotate the way that you're partitioning this cycle, and that determines if there are these boundary points in between certain pairs of points in the cycle, you'll be able to include those when the partition is rotated so that that's within one group, but not when it's between two groups. That's an earlier mechanism that I was using for setting up these tiles for variables. And this has the benefit that it can much more easily handle, this is very scalable to those wide variable tiles that you would have to have if you had much higher degrees. If you didn't have the same restrictions on the instance. Does that make sense? Okay, let's wrap this up then by doing the partition of this set. So what did we say about the we wanted to set variable 1 to satisfy that first clause. So I think that's this is clause 1 here, and this is variable 1 here in the end. So let's do that. Let's group these ones together. And like this. This is the false configuration of variable 1 because I'm covering the point on the negative side. So you can see, importantly, that I've used only 2 partitions involving the interior points of each of these tiles. And if we check that for each of the tiles, then we'll know that we're within our budget because K is just going to be the sum of all of those green numbers.
Can I just go back to my earlier question? So
yep.
The signs determine not only the tiles, but also the way you map satisfying assignments of the Boolean formula to partitions, right?
That's true. Yeah. Sorry, I cut you off before you got a chance to ask that earlier, but that is certainly true. That's right. So the signs do determine this step. So for example, if the signs were plus and minus instead, and I was constructing the partition for a satisfying assignment where V1 was false, then I would want to use the opposite version of the partition at this stage. That's right. But yeah, as we observed, the set of points itself is symmetrical in that way in this case, but not for some of the others. Okay, so next we wanted to use variable 3, which is down here, to satisfy clause 3, which is up here. So we better set that one to true, which looks like this. And again, we're using 2. And then that allows us to do this wire in this way, or this edge. I keep saying wire because they look like wires in the graph layout. This edge in this way. And in both of these cases, we have we've set up the clause with one of its boundary points covered, and that's how the clauses are designed to not quite have enough to cover their points unless one of the boundary points is covered. So they're going to be fine. Let's set variable 2 in a way that it can satisfy clause 2, which is obviously we're going to have to send the signal downwards. So that forces us to do it like this. And then the construction tells you to partition so that you include the other positive boundary point as well. But I guess you probably wouldn't have to do that in this case. But I'm just trying to come up with an example partition, so let's do it. Anyway, then I can follow this wire down using 2. Using 2 again, I can do these ones. and that's covered one of these clauses. So now if we look at the clauses, the three clauses, we have, in this case, 2 to use. We can easily partition the interior points of the tile, and in this case, we can also reach that spare boundary point that was corresponding to the negative direction if we had have alternatively satisfied this clause 3, by setting v2 to false. Let's see, in clause 1, same deal. We can do this, and then we can like fill out this wire because this point is included. We can send a signal to the variable, and here we kind of run into something weird. But remember, I'm drawing these as squares, but they're just sets that have to have a maximum diameter of epsilon. So there's actually nothing stopping me using a smaller square, or using a square that like looks like this or something that just includes this point, or even using a square like this and just saying that even though the square overlaps this point is actually belonging to this square. It doesn't really matter. We can do this fine. And this also shows you that if we had have done some weird partition here, it wouldn't have been a problem because this other clause was already satisfied. But in certain circumstances, it might be necessary to include the point with the variable so that you can satisfy the clause in that direction.
Can we not have the partition not be a partition?
Okay, yeah, sure. Just to make it clear, it's like that. Okay, the other clause is clause 2, and that one we have a budget of 3. Better draw that more clearly. We can do it like this. And then again, we have this edge tile. We have a budget of 2. We can spend it like this. And you see that we have covered every single point using k equals 2 plus 2 plus 3 plus 2 plus blah, blah, blah groups. So this is the existence of a k epsilon partition that we found by following the kind of instructions corresponding to the satisfying assignment.
I find those so satisfying.
So
Pun intended. I'm gonna give these PAR instances to my son to do sitting at his desk just for fun.
Okay. Cool. Yeah. Well, will you tell him about how Formula 1 is unsatisfiable, or will you just see if he can do it?
I'll give him an hour or so. See what he says.
Okay. I'm looking forward to you coming back and telling me. Russell came back with a paper that says that if you could solve this problem in general, you could solve any problem in the class NP.
That's right. Yeah. Yeah. Thanks a lot, Matt. Sorry, I think I jumped in there. Right. Maybe you had some final comments to make, or are you done?
Yeah. Well, the only final comment is that I'm sorry I didn't get to talk about the other direction. But if you're curious about why, in the case of an unsatisfiable formula, it becomes impossible to do this kind of construction and build the k epsilon partition. It fundamentally comes down to the fact that for one of the clauses, it's going to be well, to cover the clauses, if you can see here, to cover the clauses, the interior points within the budget, you can't afford to cover all of their boundary points. So for example, in clause 2 down here, we could do it like this. There are a couple of other ways you can do it, but you can never get all 3 of these points that are on the boundaries. You can never get all 3 of those using just 3 boxes, because if you did, then you wouldn't be able to reach this middle one. So it kind of forces there to be a variable out there that is satisfying that clause. And in more detail, that argument is made in the thesis itself. So we'll have to leave it at this, but thanks very much, everyone, for listening and your interest and questions and comments about my work. And yeah, back to you, Dan.
Yeah, thanks a lot, Matt. Are there any questions quickly? I guess not, so I'll just pause briefly. All right. So next week, Russell Goyder will be speaking about the relation between information theoretic and physical entropy. We've covered some of that, a little bit, in the past seminars. I think it's going to be really interesting, so do come along for that. And then that will be the last seminar of the year, and we'll resume on the 19th with a renewed vigor. And thanks, Matt, for this series of talks.
Excellent. Yeah, thanks for the opportunity. And I'm looking forward to next year. And next week and next year.
Sure. All right. Good evening, everyone.